Okay, let's go ahead and get started. Sorry about the confusion. I just naturally assumed that our regular room would be free, but I was wrong. But here we are. I guess in the future, if I have to schedule a makeup lecture, somebody remind me that I need to book a room for it. Okay, let's go ahead and get started. Today is going to be basically a lightning review of everything Hilbert spaces, observables, and linear algebra. It might be a bit of review. Hopefully it's a bit of review for most of you. But I think it's important to do just to establish a common language, make sure that we're all on the same page, and hopefully to at least remind ourselves of some notions that we might not remember so well. Okay, so let me just remind you that a state in quantum mechanics, the physical state of a system, is described by a state in a Hilbert space, which we could denote curly H. And a Hilbert space is basically a vector space where you're allowed to do calculus, integrate, differentiate, take limits of series, so on and so forth. In particular, the Hilbert space of quantum mechanics is a complex linear vector space in the sense that you can always take a state in a Hilbert space, multiply it by a complex number to obtain another state in that Hilbert space. Likewise, you could add two states in a Hilbert space to obtain another state in the Hilbert space. Those two properties are what we refer to as the complex linearity properties of the Hilbert space. And a little bit more interestingly, a physical state of a system is not represented by an individual state in a Hilbert space, but rather a ray in a Hilbert space, meaning that any two states in the Hilbert space, any two elements in the Hilbert space that are related by the complex multiplication by some overall constant will describe actually the same physical state. So sometimes we might even be fancy and say that physical states are given by equivalence classes of states in the Hilbert space. But that's just some fancy mathematical terminology that you could ignore if you want to. Probably. Maybe. Okay. A little more interestingly, given every state in a Hilbert space, we can define a dual state. So for every state, which is to say for every ket alpha in the Hilbert space, there is a dual ket, or a dual vector, typically denoted a bra. And given a ket and a bra, you can form an inner product. So if you have a bra beta and a ket alpha, you have an inner product, which is a complex number. Obeying two important properties. So first of all, if you complex conjugate the inner product between beta and alpha, you obtain the inner product between alpha and beta. And this implies, in particular, that the inner product of alpha with itself is real. And in particular, one of the assumptions of the Hilbert space structure is that it is positive and equals 0 if and only if the state that we're considering alpha is the null state. Where I remind you that the null state is the state which has the property that if you add it to any other state, it doesn't do anything. Okay. So that's enough about states for the time being. Operators are maps which take one state into another. So they're typically denoted, not always, but typically denoted by capital letters, and they will be taken to act on kets by multiplication from the left. So an operator A will act on a ket. So A will act on a ket by taking alpha into the state A times alpha. And operators can be added and multiplied. In the obvious way. So, for example, if you have operators A plus B, A and B, then you can define the operator A plus B as the operator which takes the state alpha into A alpha plus B alpha. And likewise, the product operator A times B is defined to be the operator that takes alpha into A acting on the state B times alpha. And two operators are declared to be equal if A times alpha is equal to B times alpha for all states alpha. So that's just a practical definition of what we mean by two operators being equal. Now, there are various sorts of operators that one could be interested in acting on Hilbert spaces. But in quantum mechanics, the most important operators are those which are linear. An operator is linear if, when you act with that operator on the linear combination A alpha plus B beta, you get, well, the obvious linear thing, A times A acting on alpha plus B times A acting on beta. Okay. However, not every operator that we're interested in quantum mechanics is going to be linear. Some operators will be antilinear. This is a bit more exotic, and you may or may not have seen it in your courses on quantum mechanics. But an operator is antilinear if, when you act on a linear combination and try and pull the constants through the operator, little a through the operator big A, you get a complex conjugation. Now, how many of you have seen antilinear operators before? Raise your hands. Can anyone give me an example of an antilinear operator? Let's see how quickly your brains are working. It is a Monday. It's 10 a.m. I've been up for hours. No one can think of an antilinear? Go ahead.
Turning kets into bras?
Well, turning kets into bras is not strictly... So remember, an operator we define as something which takes a state in a Hilbert space to another state in a Hilbert space, not into a dual state. Okay. You're thinking along the right lines. So, you know, taking a bra into a ket is an operation that takes the Hilbert space into the dual Hilbert space. Okay, that's also something you could think about. But I'm looking here for an operator which takes states into states, kets into kets. Anyone can think of one. Okay. Think of your favorite Hilbert space. What's your favorite? Someone tell me their favorite Hilbert space. Everyone's got to have a favorite. Nobody? Okay. Let's be a little more explicit. Let's think about a particle moving on a line. What's the Hilbert space that you use to represent the state of that particle in quantum mechanics? Everybody should know this one. Don't be shy. Nobody knows this one. Okay, go ahead. Yes. Or to say it a little more prosaically, if you represent the state of a particle on a line, you represent it by a wave function psi of x. Okay. Now, what operation could you do on psi of x that would be antilinear? Yes. Complex conjugation. Excellent. Okay. Complex conjugation is an example of an antilinear operator. Can anyone guess what sort of physical operations might be represented by an antilinear operator? So I'm not just introducing this to torture you. I'm introducing it because two of the most important physical operations in physics actually are antilinear rather than linear. Okay. I will not tell you. That way, if you're bored during the rest of this lecture, because it's going to be a review, you can try and figure it out for yourself. Okay. The hint is that there are two of them. You know both of them. They're very important. Okay, let's proceed. So operators also act on bras, but they act from the right. This is the miracle of Dirac notation. It's really lovely. It makes everything very nice and elegant. So it takes a bra alpha into the bra alpha times A. And it has the property, of course, that if you took the inner product between the bra alpha times A with some ket beta, then that would be equal to the inner product between the bra alpha with the operator A acting on the ket beta. Okay. So we will often drop the parentheses and just denote this as A alpha beta. And sometimes this combination, as we will see in more detail below, is called a matrix element of the operator A. Okay. Now, an important thing to remember is that, in general, the state A times alpha is not the dual of the state alpha A, of the bra alpha A. You can take the ket A times alpha and write down the corresponding dual vector, the bra alpha times A, and write down the corresponding bra, and it will not in general be equal to alpha times A. So what we do is we define the Hermitian conjugate a dagger of the operator A to be the operator such that alpha A dagger is the dual of A times alpha. And then a Hermitian operator, maybe it's an Hermitian operator, I really never know. An Hermitian operator, okay, I'll put the n in parentheses because I'm not sure. Is it a Hermitian operator? Okay. A Hermitian operator, you learn something every day, is a linear operator such that A is equal to A dagger. Now, one of the things that we should remember about the multiplication of operators in quantum mechanics is that operator multiplication is associative, meaning that the operator A times BC is equal to the operator AB times C, but it is not commutative. So AB is not equal to BA in general. And because linear Hermitian operators represent observables, this is a fundamental difference between the observables of classical physics and those of quantum physics. Observables in classical physics, of course, commute with one another. If you observe the position and momentum of a particle classically, you will get the same result as if you observed the momentum then the position. But of course, as you know, that is not necessarily true quantum mechanically. So now let me just remind you of a property. So a property that is easy enough to show is that the Hermitian conjugate of a product is equal to the product of the Hermitian conjugates in reverse order. If this is not obvious to you, prove it. This is not an exercise that you do because I assign it on a problem set. This is an exercise you do because it makes you a better person. There'll be a lot of those exercises in this class. Now, for any bra alpha and ket, for any bra, let's call it alpha and ket beta, we can define an operator which is known as the outer product and that is just beta times alpha in the opposite order as the inner product. So as you can see, this is an operator because it will act on bras from the right to give you another bra and kets from the left to give you another ket simply by taking inner product with either the ket on the left or the bra on the right, as is hopefully clear from this notation. So for example, never draw things in the right order. Beta alpha will take the state gamma into the state beta times the inner product between alpha and gamma. And so on and so forth, as is hopefully obvious by the notation. Dirac notation is pretty awesome. The operator alpha alpha is known as a projection operator. And if the state alpha is unit normalized, then this projection operator has the property that p squared is equal to p, where p is the operator alpha times alpha. And indeed, sometimes we will refer to any operator which has the property that it squares to itself as a projection operator. So a projection operator is exactly what you would think it is from your linear algebra classes. It's the operator that projects you onto a particular vector in your vector space, a particular state in your Hilbert space. And then there are two more properties that you can either believe or you can prove to yourselves if you're skeptical sorts of people. The first is that the Hermitian conjugate of the exterior product between alpha and beta is the exterior product between the dual bra and ket beta alpha. And the second property is that the matrix element of X between the bra and ket beta and alpha is the complex conjugate of the matrix element of the Hermitian conjugate of X between now the bra alpha and the ket beta. So those are both simple consequences of the definitions I've given above. There's a slightly less simple consequence, but one that you surely have already seen before, which is that the eigenvalues of a Hermitian operator are real, and eigenvectors of a Hermitian operator with different eigenvalues are orthogonal. This is why Hermitian operators are the right things to use to represent physical observables. When you measure the physical position of a particle, it's a real number. And remember that the third postulate of quantum mechanics states that the outcome of the measurement of an observable is one of the eigenvalues of the corresponding operator. And so if you want to get a real value for the position of a particle, then the observable that represents the position of the particle better be Hermitian. Shall we prove this theorem? Or would you like to do it as an exercise? You guys have all seen the proof, I'm sure. You may not have seen it in quite in the Dirac notation language. Shall I leave it as an exercise so we can blast through this? Or raise your hand if you'd like me to prove it. Okay, maybe you'll be shy because all your friends don't want to prove it. Everyone close your eyes. Close your eyes. Close your eyes. Put your heads down on the desk. Okay. Heads down. Heads down. Heads down. I can still see a few of you. Okay. Now raise your hand if you want me to prove the theorem. Okay, we still don't have a quorum. Okay, the proof is an exercise. It's in the book. Okay, let's proceed. So, any questions, by the way? I realize that I'm going through this a little quickly because it's presumably review to most of you, but hopefully it's at least still valuable. Any questions? Yes. Yes. Sorry. Any other questions? Any more substantive questions? Any less substantive questions? Yes. You had a question?
I'm not sure many will get to it. I just wonder if you could define the Hilbert space.
So far, I have not specified a particular Hilbert space because I'm trying here to introduce the general structure of quantum mechanics. Quantum mechanics says that states in any physical system live in some Hilbert space. Right now, this could be the two-state Hilbert space that describes a spin 1/2 particle. This could be the infinite dimensional Hilbert space that describes a particle moving on a line. This could be the much larger infinite dimensional Hilbert space that describes the quantum mechanics of the universe as a whole. Okay. All three of those are, although I guess we don't know much about that Hilbert space, but at least all 2.5 of those are Hilbert spaces of the sort that I'm considering here. Okay. So right now I'm trying to introduce general properties of Hilbert spaces and operators before going into particular examples. Within a page, I'll go into some examples. Yes. Good question. Other questions? Good. Okay. So, I already started that sentence. We usually normalize our eigenkets so that we label eigenkets of some operator A. So remember, the eigenkets of an operator A are those which, when you act on them with the operator capital A, you just get a number. And so usually we'll label them by some index. Say it could be n, which could either be a discrete index. It could either be a finite index that takes values from 1 up to capital N. It could take an infinite number of indices, or it could be something continuous that we have to integrate over. But we usually normalize our eigenkets so that the inner product between any two eigenkets is equal to either 1 or 0 if the two indices are equal. Where here I'm using the Kronecker delta symbol, delta NM, which hopefully you guys have seen before. Is that correct? Good. So in this case, any state, psi, can be expanded So remember that one of the fundamental postulates of quantum mechanics is that the eigenstates of any operator form a complete basis for the Hilbert space, in the sense that any state psi could be expanded as a sum over those eigenstates times some coefficient. And if these states are normalized in the way that I have drawn up at the top of this page, then the number which appears in this linear expansion is just the inner product of psi with the bra corresponding to the eigenstate. Or, if we want to say this formula a little more concisely, the operator 1 is the sum over all of the eigenstates of a given operator times the projection operator onto the corresponding eigenstate. Let me say that again. For each eigenstate of, so every operator, capital A, has some eigenstates, an, where n is some index. For each such eigenstate, you can write down the projection operator that projects you onto that eigenstate. And then if you sum those projection operators over all of the eigenstates of that operator, you will obtain the operator that does nothing at all. Okay. This is another way of phrasing the statement that every state can be expanded in terms of the basis eigenstates of some operator. And this property, as I mentioned before, is sometimes referred to as the completeness of the Hilbert space, where the word complete is some loaded mathematical word that has some stupid definition in terms of epsilons and deltas that we won't bother to get into. In fact, this formula that 1 is the sum over all of the eigenstates of the projection operator is actually an incredibly useful formal identity as far as thinking about quantum mechanics. It allows you to relate the formal Dirac notation that we have been using so far in this lecture with the traditional, more prosaic way of presenting quantum mechanics in terms of wave functions. In terms of complex functions, L2 functions, that you often see in your first course in quantum mechanics. Indeed, the quantity appearing in this relationship up here, A and psi, has a name. It is the wave function of the state psi in the A basis. Have you guys seen this before? This statement? Okay, you have seen this. If you haven't seen this, it's a set of words that bear thinking on. So, in addition to representing any state psi in a given basis in terms of its expansion coefficients, the overlaps or the inner products A and psi, one can also represent an operator x in the A basis simply by using this wonderful formula that 1 is the sum over all of the projection operators, and just writing x as 1 times x times 1, and inserting basis states, an expansion in terms of basis states on either side of x. So what do you get? Well, you get the following formula, which says that x can be expanded in the basis associated with A in terms of this set of coefficients, which I have already referred to as the matrix elements. And here they would be the matrix elements of the operator x in the A basis. And then, now there's a reason why I'm using the word matrix here, which is that multiplication of operators in this basis is equal to the usual matrix multiplication. I guess I should make multiplication of linear operators. It is the usual operation of matrix multiplication, as you are familiar with from your linear algebra classes. And if that's not obvious, prove it. and prove it as you will prove many things in linear algebra by putting ones all over the place and expanding in terms of these basis elements. And likewise, the action of an operator, and again I should say linear operator, on a ket or on a bra is the usual matrix action on a column, or alternatively a row vector from the left in the case of a ket, or from the right in the case of a bra. And that, of course, is also an exercise. It's actually worth going through all of this. So reminding yourself why it is that matrix multiplication is the same thing as the multiplication of operators as we have defined it is a useful exercise to go through. And so, of course, implicit in this statement is the statement that we can regard the wave function in a given basis as a column vector, and that's the wave function of a ket. And likewise, if we were to expand some bra in the A basis, say the state beta, so that would be the sum over n, beta an, then the wave function of a bra vector would likewise be viewed as a row vector rather than a column vector. And of course, the inner product in this case is the usual dot product. Okay, maybe I should say that. The inner product, if I could spell product, the inner product is the usual dot product. And the outer product, well, it's either usual or unusual depending on your linear algebra class, but it is the usual or unusual exterior product of a row vector and a column vector. Simply, you view a row vector as a 1 by n matrix and a column vector as an n by 1 matrix. And instead of taking the dot product by multiplying a row times a column, you multiply the column times the row using the usual rules of matrix multiplication. Now of 1 by n times n by 1 matrices. Again, work that out. That's an exercise to make you better people if you're not already familiar with this. However, I think that in this class, we're not going to be particularly focused on the expansion of our states in any particular basis in terms of row vectors, column vectors, and so forth, because very often we'll be thinking about infinite dimensional Hilbert spaces describing particles moving on spaces, for example, and it can take all day to write an infinite by infinite matrix. It's a joke. Okay, so enough of this abstract stuff. Let's go on to a few examples. Maybe before I do so, I should pause and see if there are any questions. Yes?
I was just wondering if you're dealing with like vectors and matrices, is there any physical significance tensors in this scheme, or are they?
Yes.
Okay. And would that be something I guess no, or do you have to wait?
No, sure. I mean, the first place that tensors would appear in this description would be in terms of the angular momentum algebra. The Clebsch-Gordon coefficients, for example, are the components of a tensor. Okay. In general, tensor algebra is a generalization of linear algebra where you take into account more general structures. And of course, and they do appear in quantum mechanics. They're a bit exotic from this point of view, so I think we're not going to focus on them too much. When we discuss symmetries in quantum mechanics, I will present a couple objects that are tensors, but I won't call them that. Okay. So tensor analysis is something that we won't encounter too much in this class, but it does arise. Yeah, good question. Yes. Quantum mechanics can be attacked with varying degrees of mathematical formality. I don't particularly think it's useful for a class at this level to use a lot of mathematical formalism. So we won't be using that language any more than necessary. My goal is mostly to introduce the language that you might encounter as physicists rather than the language that you might encounter as mathematicians if you end up, unfortunately, having to become one. Any other questions? Okay. Now, of course, the Hilbert space under consideration can be either finite or infinite. Finite dimensional or infinite dimensional. So far, I've written down all of these formulas using the notation of a finite dimensional Hilbert space, where I wrote things like sum on n, where n would be summed over some discrete set, so the integers or some range of integers from 1 up to n, for example. But of course, if you were going to study a infinite dimensional Hilbert space, then you might also work with a continuous index set, so a continuous basis of states for your Hilbert space, and then you would be integrating over n rather than summing over n. Now, there's a bit of a subtlety here, which is that in principle, one could integrate with different sorts of measure factors. There could be integral dn times some function of n, rather than just the integral dn. And in fact, the choice of those measure factors is part of the definition of your Hilbert space. Okay. So one does occasionally encounter Hilbert spaces where there are different sorts of integration measures that would appear when, for example, you compute inner products. To give you an example, somebody already referred to the Hilbert space of a particle on a line as the space of L2 functions. L2 here is just a fancy mathematical name for the fact that you normalize states by some formula like that, being equal to 1, or in general being finite. But there are other sorts of Hilbert spaces that one could define, and unfortunately one sometimes does have to define, where there are different sort of normalization conditions that you would impose. For example, if you're studying a particle moving in a potential, but that potential goes off to minus infinity somewhere, or plus, then in some cases one has to revisit this notion of precisely how you normalize the states in the Hilbert space. I believe in this class we may not have to encounter that, but it's something that you should keep in mind. Simply that the choice of integration measure is part of the definition of your Hilbert space. Okay. So let me just remind you of a few examples of Hilbert spaces, presumably examples that you have seen before. So for an example of a finite dimensional Hilbert space, I'm going to first introduce you to the following slogan, which is that when we quantize a classical system, the dimension of the Hilbert space is roughly given by the volume of the phase space of the corresponding classical system. Now, there's something obviously wrong with that equation that I've written there. So the dimension of a Hilbert space is a dimensionless quantity, whereas phase space the volume of phase space is dimensionful. It has units of x times p. So I need to introduce some dimensionful quantity in order to make the dimensions of this slogan work out. And the dimensionful quantity I introduce, of course, is h bar. H bar has units of action. So I'm going to be measuring the volume of the phase space in units of h bar. Okay. So right now this is just a slogan. It may be one that you've seen before. It's a slogan that we will derive later on in this class when we consider semi-classical and WKB approximations. But for right now, I just want to introduce it as a handy mnemonic for guessing what sort of systems would have a finite or an infinite dimensional Hilbert space. So for example, a spin 1/2 system or a two-state quantum system has, well, it has two states, which we will often denote as either plus or minus, or up and down. And then the statement that this two-dimensional Hilbert space is complete, is the statement that, for example, the operator 1 is the sum of the projection operator onto plus, as well as onto minus. And there are various other sorts of operators that we can introduce in this Hilbert space. For example, if we're thinking of a spin 1/2 system, then the spin in the z direction would be given by, well, some constant, which is more or less conventions, times the matrix with 1 and -1 on the diagonal, and zeros elsewhere, which, when written in the Dirac notation, is the linear combination of the projection operators with a relative minus sign. So this would be an example of a system with a finite Hilbert space. An example of a system with an infinite dimensional Hilbert space would be obtained by quantizing a system with an infinite volume phase space, such as that of a particle on a line. So in this case, of course, the classical observables, x and p, get promoted to quantum operators, which we sometimes denote x hat and p hat. There is a basis of states, also labeled by the continuous parameter x, which are the eigenstates in the x basis, which are normalized such that the inner product between any two of them is given by a Dirac delta function. So remember that for a finite dimensional Hilbert space, I use the Kronecker delta. For an infinite dimensional Hilbert space, I use the Dirac delta. And as before, there's implicitly some choice of measure when I write down this continuous Hilbert space. And for other choices of measure in the integration integral dx, I might have to include some function of x and y that would appear in front of this delta function. But for the sorts of things that we're considering now, just the normal Dirac delta function would suffice. But for example, as an example of a case where you would have a non-trivial measure factor in front of the delta function, you could imagine, say, a particle moving in 3 spatial dimensions. But instead of writing it in Cartesian coordinates, you could write it in radial coordinates, where the 3-dimensional Dirac delta function for x then becomes a Dirac delta function for r times some function of r. It's like r squared. Okay. So there are cases where you will have to take into account non-trivial factors that would appear in the normalization. Then the statement that this is a complete Hilbert space is the statement that the operator 1 is the integral over all projection operators. And then a general state psi could be expanded in terms of these basis states. And the overlap between x and psi, the inner product between x and psi, is the thing that we usually call psi of x. I will, in this class, mostly use the notation just the inner product between x and psi rather than the function psi of x, because it makes the Hilbert space structure a little clearer. Yes, question?
It seems funny that the position eigenstates are in the Hilbert space, because you get 2 bases of different sizes.
Yeah, there's a... when you have infinite dimensional Hilbert spaces, there are all sorts of subtleties like this. I mean, technically speaking, you need to be careful about what is and isn't in the Hilbert space. Technically speaking, a Dirac delta function is not a function. Okay, it's some sort of funny mathematical object called a distribution. But we're physicists, not mathematicians, and so. As physicists, we're going to choose to ignore all of these mathematical subtleties until we have to, which say never, thankfully.
Okay, and not all states are physical states. I mean, you find that you can combine any two states and get a new state that's a physical state?
Yes, you could, for example, yes.
Oh, so what about the null state? That's not a physical state.
That's not a physical state. That's correct.
Not
So
a Hilbert state?
the null state is, the null state does not represent, okay. Physical states are represented by rays in a Hilbert space. And I suppose technically in the definition of a ray, I should say that any non-null state in the Hilbert space defines for you a ray in the Hilbert space, okay, and hence a physical state. So the null state does not represent any physical state. I want to distinguish here, I was very careful to call the null state 0 times another state alpha, rather than a state that looks like that, okay? Because if you consider, for example, a harmonic oscillator or some other particle in a potential, we often use a state like that to refer to the vacuum state, which is a physical state. The null state is not the vacuum state. The null state is the state that, it's like in a vector space, it's the state all of whose components are 0. Not the
So
same.
Hilbert space is sort of like states with the 0 vector?
Yeah, that's right. That's right. Think about the plane. The Hilbert space is the plane, the two-dimensional. This is not me doing the sign of the cross. This is me doing the coordinate axes of a two-dimensional plane. Think of a two-dimensional plane. Then the Hilbert space is the set of all vectors with finite norm in a two-dimensional plane. Okay. And physical states then would be rays, would be literally rays in that two-dimensional plane. Questions? Okay. So likewise, one could expand the corresponding bra vector in this basis. And the expansion coefficients here then would be the wave function for the dual state, which, as you can check, based on the properties of the inner product, is now the complex conjugate of the wave function psi of x. And then the inner product of a state with itself is precisely, well, let's use our favorite trick. It's psi times 1 times psi. And using this expression for 1 is the integral dx of, well, psi star psi, or the absolute value of psi squared, which will be set equal to 1 for a normalized state. And then the inner product between two generic states, say psi and chi, is then just the integral dx of the wave function psi star of x times chi of x dx. And that's either called the inner product or the overlap between those two states. I'll use the words overlap and inner product interchangeably. It's called overlap because if you were to literally draw these wave functions, let's assume they're real for a minute. If you were to physically draw these wave functions as a function of x, then this integral of psi times chi that I'm writing here would be literally something closely related to the amount of a measure of the amount of overlap those two graphs have with one another. So the sort of operators that one can define on this Hilbert space include the operator x hat, which is defined as follows. So it's easiest to define the operator just by working in the x basis. So it's the integral dx of x times the wave function psi of x times the basis state x. So that defines the action of this operator x. In particular, it multiplies the wave function by x, now as a function of x. Okay. So in particular, it takes the wave function psi of x and gives you x times psi of x. Okay. There are a lot of x's floating around here. It's important to keep your mind clear. Okay. Take a deep breath. Look at all the x's one by one. Hopefully it should be clear. Another more interesting operator would be the derivative operator, whose action on a state psi is defined by its action on the wave function. In particular, it'll be the x derivative of the wave function in this basis. And it's easy enough to check that this derivative operator, as I have defined it, is anti-Hermitian. So the way that we show this is by using integration by parts. So let's show that. So let's imagine computing the matrix element of this derivative operator between a bra and a ket. So then by definition, this is the integral dx of the wave function for the bra chi times the derivative d by dx of the wave function for the state psi, that we can then integrate by parts to obtain minus the integral dx of d by dx of chi x times x psi. Now, in this integration by parts, there is, technically speaking, a boundary term that we have to worry about. But our Hilbert space consists of those states described by normalizable wave functions, whose integral dx of the wave function squared vanishes. This means that all of the psi's have to vanish sufficiently quickly out at infinity that I don't have to worry about these boundary terms. So I'm just left with this integration by parts term. And then I can notice that this is just minus the complex conjugate of the matrix element of the operator delta between the bra psi and the ket chi. How do I notice that? Well, you just take this thing and you move it onto the other side of the equation, okay? And you compare it to this expression up here with psi and chi replaced. And you see that in order to get those two expressions to be equal, you just need to switch each of the kets. You just need to take the complex conjugate, which switches a bra and a ket in an inner product. And this quantity that I've written here is otherwise known as the matrix element of the operator, which is the Hermitian conjugate of delta. So the implication then is that because the matrix elements of the operator delta are the same as the matrix elements of, sorry. I forgot to reverse those guys. That's hopefully why you were looking confused. So, because the matrix elements of the operator delta are equal to the matrix elements of the operator minus delta dagger, that means that delta is equal to minus delta dagger. Remember that two operators are declared to be equal if their action on any two states is equal. And so the operator delta is anti-Hermitian. And so one can define an operator which is Hermitian, and therefore a candidate for a good observable, by multiplying delta by I. And we conventionally include a factor of h bar to give this quantity units of momentum. And this, of course, is the momentum operator. And if we wanted to, we could go ahead and rewrite everything in the momentum basis rather than in the position basis. And in the position basis, remember, that the operator x is simple. It's just multiplication by a function, whereas the operator delta, derivative operator, is not. Likewise, in the momentum basis, the operator p is simple. It's just multiplication by the function p, whereas the operator x is not. So if you want a nice little exercise, write the operator p as an infinite by infinite matrix in the x basis. Okay. You know that how to compute its matrix elements. So just think about how you would write it in the x basis. You'll have to think a little bit about how you would like to define infinite by infinite matrices. Okay. But it's a nice exercise in going between these different ways of thinking about Hilbert spaces. Any questions? No questions? Okay. So let me continue with a few more words about observables. So I remind you that an observable A is a Hermitian operator and that the third postulate of quantum mechanics states that if the observable A is measured in the state psi, then the outcome of the measurement will be one of the eigenvalues of A, and the probability of a given eigenvalue is the square of the overlap between psi and the corresponding eigenvector. Where here in this formula, I'm assuming that all of my states are, A, are unit normalized, and the state A is one of the eigenstates of the operator A. So an exercise for you is to figure out how this would change if I don't normalize things. Write down the appropriate formula if the states are not unit normalized. That should be pretty easy. And I will define the expectation value of A to be the matrix element of A between the bra and the ket psi. So this is referred to as the expectation value of A in a given state. And in order to understand why we call it an expectation value, let's use our famous formula that 1 is the sum of projection operators. So I'll write this as the sum over n and m, psi times an times the matrix element an, am, times the wave function now as a function of m rather than n. This quantity here, of course, is equal to an times delta nm, or am times delta nm. They're, of course, the same thing. And so this whole thing is just equal to the sum over n, an times the overlap between psi and an squared, otherwise known as the probability of observing the eigenvalue an. So the expectation value of n is the sum over all possible outcomes of the observation times the probability of a given observation. So this is what we normally call an expectation value, not just in quantum mechanics, but in probability. So this is normally what you would think of as the expected value of some probabilistic variable, given some probability distribution. Now, two observables are said to be compatible if they commute so that, for example, A and B would be compatible only if the commutator AB minus BA is equal to 0. And in this case, they can be simultaneously diagonalized. Meaning that one can take as a basis for the Hilbert space some set of states, I'll call them AN, BI, which are simultaneous eigenstates of these two compatible observables. So that A times one of these states, AN, BI, would be AN times that state, and likewise B acting on it would give you BI. And I'm using N to run over the eigenvalues of A, and I to run over the eigenvalues of B. Now, if it's not obvious to you that two commuting observables can be simultaneously diagonalized, prove it to yourself. Okay. You don't have to give a mathematical proof, but think about why it has to be true. Now, otherwise, if the two operators do not commute, the observables are incompatible. And much of the mystery and confusing aspects of quantum kinematics comes when you consider incompatible observables. So the most basic observation of this sort is the Heisenberg uncertainty principle, which is formulated in terms of the variance of the expectation value of an operator. So given an operator A, or given an observable A, we define the variance of that observable in a given state to be it's usually called the expectation value of delta A squared, where delta A is the operator, that is the difference between A and its expectation value, which one can easily check is just the difference between the expectation value of the operator A squared and the square of its expectation value. So I want you to pause for a minute and prove to yourself that that first line is equal to the second line. The expectation value of the square of the difference between A and its expectation value is equal to the difference between the expectation value of A squared and the expectation value of A squared. That pause is important. Okay, let's pause and stare at it for a minute. Everyone done staring? Okay, questions? Yes.
By uncertainty principle, you can't measure a particle speed at a certain point, right?
What's that?
You can't measure a particle speed at a certain point.
Yeah, well, I'm going to get to the uncertainty principle on the next, in literally 0 seconds, unless there are other questions. Okay. 0 seconds over. We can now state a basic theorem about Hilbert spaces and expectation values of operators, which is that in any state, the variance of the operator A times the variance of the operator B is greater than or equal to 1/4 times the absolute value of the expectation value of their commutator squared. And this is known as the Heisenberg uncertainty principle. So, one important special case of the Heisenberg uncertainty principle is if the commutator of A and B is proportional to the identity operator, namely if it's a number rather than an operator, so let's call it, C, then the left-hand side, then the right-hand side of this equation is independent of the state that you're in, because if the commutator of A and B is just a number, then the expectation value of a number is just that number. Okay, it doesn't depend on what state you're in. So then we just get the quantity C squared divided by 4. Okay. And so the nice thing about this is that the right-hand side is independent of whatever state you're in. So it's some general constraint on the product of the variances of these observables that is independent of whatever state you're in. So it's some universal property of observables in quantum mechanics. So how many people have seen this particular formulation of the uncertainty principle? Okay, you guys, good. How many of you would like to see me prove it? Okay. Anyone? Raise your hands high. Do I need to ask you to put your heads on the desk? No, nobody's ashamed at this point. How many people would like to raise your hands high if you would like me to prove it? 1. Okay, high. High means high enough that I can see it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many people do not want me to prove it? How many people would not like to see it? Would you be bored and you would tear your eyes out in frustration? Just like Odysseus. Was it Odysseus or Orpheus? Oedipus. It was Oedipus. Okay. No one's going to tear their eyes out. I'll go ahead and prove it. Okay. The proof of the uncertainty principle is just one of those technical proofs that I can't really come up with any beautiful, elegant, lovely physical intuition for. You just got to write down a bunch of equations and convince yourself that they're true. So the proof proceeds in 2 parts. The first is that we have to prove what is known as the Schwarz inequality, which is the statement that the product of the norms of 2 states is always greater than or equal to the absolute value squared of their overlap. Okay. That's actually not a particularly surprising statement. Okay. For example, if you take alpha and beta to be unit normalized, it says that the overlap between them is always less than or equal, has absolute value less than or equal to 1. If you just think about vectors on a plane, it should be pretty obvious. If you take 2 unit vectors and you compute their dot product, then that dot product is the cosine of the angle between them, which is always less than 1. Okay. And it's also true for Hilbert spaces. Shall I prove it? No. Nobody wants me to prove it. Yes? Raise your hand. Nobody wants me to prove it. Okay. So given the proof is an exercise, given the Schwarz inequality, well, actually, given the Schwarz inequality, it's pretty easy. Just let the state alpha be the operator delta A acting on psi, and the state beta to be the operator delta B acting on psi, where, of course, delta A is A minus its expectation value in the state psi, and likewise for delta B. So let's go ahead and write that down. then what do we get? Well, we get that delta A squared, the variance of A, times the variance of delta B, so just writing down the left-hand side of this equation, is greater than or equal to the absolute value of the expectation value of the operator delta A times delta B. Right? Just writing down that formula for this choice of states. And I'm also using the fact that A is Hermitian, okay? Because technically speaking, that should be delta A dagger here rather than delta A. And so I'm using the fact that A is Hermitian, and because the expectation value of A is real, then the difference between A and its expectation value is also Hermitian. So that delta A is Hermitian, so I can forget about that Hermitian conjugate. And what is that? Well, the product of any two operators, delta A and delta B, can always be written as the sum of 1/2 times their commutator and their anti-commutator. Okay. So that is 1/2 times the expectation value of their commutator and 1/2 times their anti-commutator. So you all remember that the anti-commutator is AB plus BA? Everyone remember that? Now, raise your hand if you want me to define the anti-commutator. Okay, nobody. Good. Okay. And in particular, it's easy enough to check that for Hermitian operators, this guy is going to be imaginary. And this guy is going to be real. So, for example, the commutator of any two Hermitian operators is an anti-Hermitian operator whose expectation value is imaginary. You're going to prove that on your problem set if you haven't already. It's easy. And the anti-commutator of any two Hermitian operators is always real for very similar reasons. So the anti-commutator of any two Hermitian operators is always Hermitian. Okay. Prove that if it's not clear. And so the expectation value will always be real. So you've got the absolute value squared of an imaginary plus a real quantity, which is always greater than or equal to just the square of that imaginary part, which is 1/4 times the square of the expectation value of the commutator of A with B. Of delta A with delta B. But the difference between A and delta A and B and delta B is, of course, just a number. Numbers commute with everything, so we can forget about them in the commutator. And that's, okay, what do you say? Quid erat demonstratum? Good. Okay, let me just, okay, I don't want to rush through that. Let me see if there are any questions. So, of course, the most famous application of the uncertainty principle is the energy position momentum uncertainty relation, which says, for example, that if you're considering a particle moving in one dimension, then because the commutator of the position and momentum operators is the constant IH bar, then the product of the variances will always be greater than or equal to h bar squared over 4. And this is, of course, the original form of the Heisenberg uncertainty relation, which leads to the intuitive statement that you can either measure the position of a particle or the momentum of a particle, but you can never measure both simultaneously. And the better you measure one, the worse you better measure the other. Or, to say it a slightly different way, if I measure the position of a particle very precisely, then the more precisely I measure the position, the greater the uncertainty I have in the momentum of the particle. Question?
Doesn't this mean that position eigenstates aren't physical?
Position eigenstates are not physical states. Check. that they're square, they're not in L2. Okay. Check that.
They're in the Hilbert space.
Well, I mean, it depends on exactly how you, well, okay. It depends on exactly how you want to try and define them. Okay. Let me say it this way. Compute their norm squared and ask whether it's finite or not. You'll find that it's not finite.
So you're saying it's not right?
It's not in the Hilbert space. Well, yeah. It's technically not. It's not in the Hilbert space of L2 functions. It is some auxiliary object that we use to construct that Hilbert space, if you want to say it that way. The Hilbert space is defined to be the set of functions which is square normalizable. And delta functions, by definition, are normalizable but not square normalizable. The integral of a delta function is 1. Okay? The integral of a delta function squared is infinity. Okay? So they're not in the Hilbert space. You can't define exactly a position eigenstate by that definition, but you could define things that are arbitrarily close to position eigenstates. Okay. So then the question of whether you include the position eigenstates as actual physical states is the question of whether you want your Hilbert space to be complete in the sense that the limit of any series of states should also be a state in the Hilbert space. And that gets into mathematical stuff that, let's put it this way, it's outside of things I want to talk about in this course. That's always the easy answer, yes.
So if you measure position and you get a value, then where do you start the time evolution from? Not a position eigenstay.
You start, well, according to the standard rules of quantum mechanics, which we'll revisit when we discuss measurement theory, you collapse the wave function of the state, and you start in a position eigenstate. And a position eigenstate has an infinite value of variance of the momentum, according to this formula. Sorry, and likewise, a momentum eigenstate has an infinite amount of variance of the position. So, I'm going to weasel my way out of this question by saying that, of course, we never measure these things with complete absolute precision. Therefore, we never collapse the wave function, if you force me to use those words, into a state that is exactly in a position eigenstate or a momentum eigenstate.
That goes against the rules, though, right? You can never, even this says that you can't, right? Like in principle or anything, you cannot measure.
I guess I'm not.
Be a certain position, like one position.
Well, we never measure anything with absolute precision. That's a mathematical construct that doesn't match what's actually going on in our physical observations. We measure the position with a certain amount of accuracy, with a certain amount of uncertainty, and then based on that, we have a lower bound on the uncertainty and the momentum. Now, as a mathematical abstraction, we could consider imagining position with absolute accuracy, in which case we would have infinite uncertainty for our momentum. But as always is the case when we have zeros and infinities, those are mathematical abstractions that don't correspond to physical reality. Now, I had to use the word collapse of the wave function, so I'm feeling very uncomfortable, so I need to go wash my mouth out right now. Maybe before I do so, there'll be some other questions. Okay, see you on Wednesday. By the way, just as